Good morning, good afternoon, everyone. Welcome to season four of the biogas workshop. And then the topic for season 4 is innovation in biogas technology, advancement and future trends. Thank you for everyone who's joined. Tusani is also in the chat. My name is Fubano Lusani. I'm going to be facilitating today's session. I'm wearing my PPE because I work with Medium Waste on small scale biogas system. So I'm very interested to know, to hear insights from our speakers. We've been working for decades on large scale biogas systems. And let's also make this networking session. So on the chat, just drop who you are, what you do, and also anything you're looking towards to on the session, or if you have any questions. Okay, so let me just break down how the session will work like. So the first thing, I'm going to introduce our speakers. We have 2 speakers, and then they're going to have approximately 20-25 minutes each. And then if you have a question, just drop it on the chat as well. And then we'll make sure to have open discussion at the end of the session. This to ensure that, for instance, the first speaker might mention something and you have a question, but it might be answered by the second speaker. So your questions will have them at the end of the session. Okay. And let me also mention that this session is also being recorded. It's available on YouTube, SABIA. So please like, share, and subscribe. Okay, let me introduce our first speaker.
Wait, I don't think Patrick is, Moses is here yet. So you can start with Patrick then.
Okay. Let me introduce our first speaker, which is Dr. Patrick Mukumba. So Dr. Patrick Mukumba is a senior lecturer in physics at the University of Ford Hare and an NRF-rated researcher. Dr. Mukumba holds a PhD in physics with a focus on renewable energy, as well as master's in renewable energy engineering. His expertise spans from biomass and biogas technologies, gasification, solar wind, hydro, and storage solutions, such as batteries, fuel cells. In addition to his extensive research contribution, he supervises both master's and PhD students, advancing in academic knowledge and innovation in renewable energy. Dr. Mukumba highlights the importance of biomass and biogas in advancing Africa's clean energy mix. Today, we will share his advances and insights on emerging innovation and future trends in biogas technology. So, welcome. And we're going to kindly ask you to summarize years of experiences in 25 minutes.
Good morning, everyone. Thank you very much, Chairperson. My name is Patrick Mukumba from the University of Fort Hare. So I will start with the introduction, followed by innovations in biogas technology.
For the sake of time, you can just give through the introduction to the innovation in biogas technology.
No.
Since our
Introduction.
Yeah.
Okay. So I'm going to explain all the aspects that are on the screen up to references. The first part, biogas industry has emerged as a vital contributor in the transition towards a sustainable and low carbon future. With the growing focus on net zero renewable energy sources, significant advances and innovations in biogas production have been witnessed in recent years. So the diagram, that one, figure 1, it shows the process flow of anaerobic digestion, whereby we have got our digester producing biogas, and the biogas is being upgraded to biomethane, as shown on the diagram. So there's need now to optimize biogas production so that we increase our amount of biogas produced. So meaning that now here, we have got traditional biogas digesters, we have got common biogas digesters, even in South Africa, fixed dome digesters, floating drum, plug flow, and CSTR digesters. But now, as we're interested in the innovation in biogas production, because we want to increase biogas yield, so meaning that now our innovation is mainly based on temperature control, because biogas production is affected by temperature. So biogas digesters have the potential to deliver biogas at a high efficiency because of better infrastructure, control of heating, and other operating parameters. The temperature within a digester is one of the main conditions for the proper functioning of methanization. This must be between very specific temperature ranges. And our innovations in biogas technology, we look at solar-assisted biogas digesters, solar-assisted biogas digesters, so meaning that we can optimize biogas production by using a solar PV system or using a solar heater, or we can use sawdust to optimize biogas production. These are new innovations. We can also use a greenhouse temperature control systems. So on the diagram there, your fig 2, you can see that now there you want to optimize biogas production. In that case, we're using a solar thermal collector, whereby now we have got a digester, and that digester now it has got some copper coils. So water from the solar geyser flows to the digester, and then now we set the temperature that you require for the digester to operate. For example, you want your digester to operate at 35 degrees Celsius. So meaning that now the water flows to the digester, and at 35 degrees now, your digester can function. But now you can use systems like, later we're going to see that we use an Arduino system, or you use a programmable logic controller to ensure that now the temperature remains at 35 degrees Celsius, or if you want the temperature to be between 30 to 35 degrees. But now your source of heat is coming from the solar thermal collectors. In this case, it's a solar geyser. So you can find that now the system now, when temperatures are above 35 degrees now, it means that now a message is sent to the bore valve. And now, at the end now, then there's no flow of water. So meaning that now, at the end, your temperature within the digester is kept at 35 degrees, not above or not below, because you've used a system. Later, we're going to explain these systems, the AI systems that you can use in the control of temperature within a digester. Like water now, in this case, you're using water as a source of heat. And also, in this case, you're using a solar system in order to optimize biogas production. And in this case now, you've got a solar system, so meaning that now electrical energy is supplied to the heating element. So in this case, you need a heating element, it can be a 12-volt heating element, or a 24-volt heating element, or it can be a 48-volt heating element. So you've got a solar system, your solar supplies electrical energy to your battery, and your battery now has to supply electrical energy to the heating element. But now the heat or the temperature is controlled now by a thermostat, So you need to put a thermostat to ensure that now it controls the temperature now. You want to set your temperature, for example, at 30 degrees. So meaning that now that thermostat is supposed to control that one, the temperature. But your slurry or your biogas slurry is being heated by a heating element, which can be 24 volt, 40 volt, or 12 volt. So here in this case, we're using solar modules. And also, this one is another new innovation in biogas production or in biogas technology, whereby you have got your biogas digester producing biogas, and now the biogas can be purified to biomethane. And now you biomethane, now you can power your generators using biomethane. And now the electrical energy from the biogas generator can now be used to supply electrical energy to the heating element. And now you can set the temperature at which you want to produce your biogas. But you find that now in this case, your electrical energy is coming from a generator, and that generator is powered by your biogas, by biomethane. So the electricity now goes back to the digester, whereby biogas is produced at a particular temperature, at a particular temperature at mesophilic stages. And now we have got another innovation because most of the digester failures that are taking place as a result of temperature fluctuations, like in winter. So maybe that now you can also optimize biogas production by sawdust insulation of your digester. You can just build your digester like your Fig 4A or your Fig 4. You can see this is a digester which was constructed, and now you have got your first wall and your second wall. So you have to put sawdust, and you can find that now your digester now is covered by sawdust. So you can find that now here you can produce biogas maximally or optimally because there are no temperature fluctuations because of use of sawdust. And also, these are innovations that can happen on the market. Here, you are optimizing biogas production by using a greenhouse envelope, so that your digester is covered by a greenhouse envelope. So greenhouses absorb solar energy through the greenhouse effect principle. When the short wave solar radiation enters the room through a sunlight plate with high transmittance, it becomes long wave radiation after being reflected from the ground. Because greenhouses block long-term radiation, compares long wave radiation is absorbed by the air in the greenhouse and in the door, and indoor temperatures rise. So you can find that now you've got your greenhouse here and you've got your digester, like your Fig 7. You can see this one is a greenhouse or a greenhouse cover, and inside there's a balloon digester. So you can produce biogas maximally here, and this setup was done, and you discover that the temperature within the digester was 30 degrees. So meaning that the temperature was constant because of the greenhouse. So here, you want to produce a biogas. You have got your your biogas feedstock. And you have got to digest. And you find that now, biogas is a composition of carbon dioxide and methane plus hydrogen. So you can find that now, since from biogas we produce carbon dioxide, there's carbon dioxide and hydrogen. So it's necessary now to introduce hydrogen into the biogas, so that the hydrogen we are introducing now can combine with the carbon dioxide to form methane. So meaning that at the end of the day, the carbon dioxide that can affect the compressibility of biogas, the carbon dioxide is now combined with hydrogen to form biogas. So you can find that now at the end of the day, from this digester, you can produce almost 95% or 99% of biogas, which is mainly methane. It's because of the introduction of hydrogen into the digester, which combines it with carbon dioxide. So that's biogas production now. You've increased the biogas production. You've increased the methane content in the biogas because of the introduction of hydrogen. But later we're going to discuss how some organisms can combine hydrogen and carbon dioxide for methane, because at the end you want to increase methane yield in biogas. And also now, it's a multi-stage anaerobic digestion, meaning that here you can find that now sometimes your biogas production is very low. So we're saying that now multi-stage anaerobic digestion is a process that breaks down organic waste into biogas by dividing the digestion into separate stages, allowing for better control over the microbial activity at each step, resulting in improved biogas yields and a more efficient conversion of organic waste compared to a single stage process. So since we're saying that now, we're doing a lot of innovations in biogas technology. So meaning that now, we need to have some hybrid systems whereby you can combine biogas with wind energy, or biogas with solar energy, biogas with even hydropower. In this case, we have got your biogas digester, and you want to form a hybrid system of biogas and wind. So now here, we know that biogas production is low in the winter, but during winter season, this is when we have got a lot of wind. So meaning that now you want to optimize the energy that is produced. So meaning that here we have got your wind turbine, which is producing electricity. And here you have got your biogas, and your biogas now, you purify the biogas into biomethane, and you feed the biogas in a biogas generator. And now you've got electricity now coming from the biogas generator, and also you've got electricity coming from the wind turbine. But also I have put this system, the ZX leader instrument. This instrument is important when you want to do a wind source assessment, because for you to have this wind turbine now, you are supposed to assess how much wind is in that locality. You want to assess the velocity of wind. You want to assess at what height are you supposed to put your wind turbine. So you need to use this ZX liter instrument, showing that you have got a wind there, a wind turbine, and a biogas producing electricity, and now you're able to drive a lot of devices using electricity from biogas and from wind. Because you find sometimes our biogas may be intermittent because of temperature fluctuations. And now here, it's a hybridization of solar and biogas. So as I have said, that we need to have some hybrid system whereby biogas production sometimes slow, and you need to assist the biogas system with other renewables. So in this case now, you can have what your solar modules here and producing electricity, and now you've got also your biogas being produced from the digester, and also you purify the biogas, and then you feed it into a generator, and then you produce your electricity. So now you have the electricity from biogas and the electricity from the solar PV system. But you cannot just buy these solar modules. You have to size your digester according to the availability of substrates, and you have to size your solar modules according to irradiance in that area and according to the energy demand in that area. And in this case, already this has been done. We have got different upgrading technologies. We have got a raw biogas with methane, carbon dioxide, water, hydrosulfide, and hydrosulfide should be removed, and other impurities in biogas are supposed to be removed. And then you purify the gas and compression, and then you store the biogas. So I have outlined some common upgrading technologies in the biogas technology. But now, since we are saying some innovations in biogas technology, so meaning that now, in this case, we want to use green energy or green upgrading technology, meaning that now, you want to upgrade biogas using green technology. So you can check now, in this case, you have got your solar for, you check your for example, your B. So biogas upgrading technologies, utilization of micro algae. For example, if you check your B, effect B, you can see that you've got solar module and you have got a wind turbine. So you want to produce hydrogen, what you call green hydrogen, from wind and solar. So when you pass electricity through wind, when you pass electricity through water, by using electricity from wind or using electricity from solar, you produce hydrogen. So now you need that hydrogen now so that you combine the hydrogen with carbon dioxide to produce methane. Or in this case, you think a biogas upgrading by microalgae.
Sorry, Doc. So just a reminder that there's 5 minutes left. So
Okay. So you can find that now here we're using green technologies for biogas upgrading because we want to produce hydrogen that we can combine with carbon dioxide to produce methane gas. And also we have got biomethane production or auto control methods. You find that now we have got some challenges because when you produce biogas, you will need to purify biogas, whereby you're supposed to remove hydrogen sulfide. But the problem that we have, if you remove hydrogen sulfide, you find that now the biogas can no longer smell. And then the end now, it's a disadvantage now when there are leaks. You are producing your biogas, but that biogas, you're upgrading it, and now it cannot smell. So meaning that now we need to put some odorants so that now you're able to detect whether there is a leak or not a leak. So you can find that now here we will use different odorants like tetrahydrothiophene, THT, so that your biogas, which has been purified, is able to smell. And there are reasons why you add some deodorants. And also now, you find that now, we also have some challenges when you compress biogas into these cylinders. We are not supposed to use LPG cylinders for bottling the biogas. We have got suitable cylinders for biogas storage. And you find that now, on the market now, you find that now, we have got new biogas cylinders for biogas, which are being made because biogas is mainly methane, and the liquefied petroleum gas that we commonly use at our homes, it is a mixture of butane. It is a mixture of butane and propane. So the properties of biogas and liquefied petroleum gas, which is a non-renewable fuel, they're different. So means that now there are new technologies whereby now we have got new biogas cylinders. So like this is LPG and this is biogas cylinder. So you can find that now we can also use this one for biogas storage. But now you find that now you are supposed to do a lot of changes so that this container or this bottle is able to store biogas. And you check the pressures of biogas and LPG, they are different. So therefore now we need to check on the market the right bottles for biogas. And also we can also manufacture new storage devices for bottling the biogas. And also we also have what you call a digitalisation and automation in biogas plants. So you find that now, when you have got your biogas system, you don't need to go there and every day and measure pH, every day and measure biogas production, every day to measure temperature of biogas. You go at 10 o'clock in the morning, 10 o'clock in the evening, 1 o'clock. You're just all the time are going to measure biogas production. But now we have got digitalization and automation, whereby you put your equipment, and the equipment can measure the biogas, and the equipment has got a storage system that is, it has got an inbuilt data logger. So meaning that now we're saying that now artificial intelligence algorithms analyze a vast amount of data in real time, enabling operators to optimize biogas production, predict equipment, and reduce downtime. So you've got Internet of Things, such as smart sensors, actuators, providing real data for monitoring and the control and optimization purposes. So this makes life easier. So you can find that now, like I was saying, we've got smart sensors. You can just install some smart sensors, and you can find that now they're able to measure, okay, the temperature of biogas is 35 degrees. And you can find that now information is stored, and you can download the information anytime that you like. And also we have got a biogas digital twins. It's also another system that you can use to optimize biogas production. And also we have got also programmable logic controllers. You can just, like I said this before, it's like water is flowing from the solar heater into the digester. But how does the digester know that now? The temperature is 35 degrees. So you need to put these systems now, the programmable logic controllers or Arduino technology, Arduino circuit, so that you can just tell that the temperature now is enough. It cannot be above or below, so it can control the flow of water. And also, there are some benefits of programmable logic controllers when you are using them in biogas systems. So it improves the safety, enhances the sustainability, and predictive maintenance. We're able to predict what is going to happen, you see now. And you're able to maintain your system. You can actually see that, okay, my system, the pH is becoming low. So what should I do? My temperature is becoming low. What should I do? The methane yield is very low. So what should I do? So by using these artificial intelligence systems, and this is a block diagram of a programmable logic controllers, meaning that now you can, after when data is collected, it can be stored, and you're able to download the data which has been stored. And also, we have got examples of artificial intelligence, the biogas, you can buy those softwares, the biogas mass software. You can just buy it, and you can just use it, so that now we're able to even to simulate your system and even come up with a model for the operation of your system. And you can also buy this software, digester performance monitoring AI system. You can also buy that software. So meaning that now, us at the moment now, we're talking of green hydrogen. And you find that now, we're saying that now we need the green hydrogen now, which can come from renewables. And you find that now, because our tomorrow is based on hydrogen. And that hydrogen now, that we are supposed to produce, is supposed to be used for biogas production. We combine the hydrogen with carbon dioxide to form methane. So meaning that these are future trends in biogas production, because at the end of the day, you need this hydrogen. So it's very easy to produce hydrogen. You produce hydrogen using renewables. And also, here is just a diagram showing production of hydrogen from, also I've mentioned this one, from water by using wind and solar. And also here, hydrogen production methods based on solar and wind. And at the end, you've got hydrogen there, and you also combine with carbon dioxide to form methane. So here also hydrogen production methods. So you have got many methods, you see now. So meaning that now our future now, we don't work at the moment. There's a lot of hydrogen that is produced from coal. But now, you find that now we need a renewable energy, green hydrogen, a renewable energy, hydrogen. So meaning that the future now is use of hydrogen in biogas plants so that you optimize methane production. And we have got, these were different methods for hydro production so that now we increase our methane production from biogas digesters. And also, these are different methods, hydrogen massive production from catalytic steam reforming of methane. So our biogas, in conclusion, biogas innovations from solar PV, solar thermal collectors, sawdust insulation, and greenhouse cover on biogas digesters. And also, you have upgrading systems, but we're worried with what? With the common ones. So you have new biogas upgrading systems that involve use of renewables. So this is the conclusion and references. Thank you very much for your attention.
Thanks, Doc. This is what happens when you ask a river of knowledge to present. Great presentation. So I noticed a few questions on the chat. We're gonna just keep them for the Q&A at the end. I'm also gonna make sure that I read through them in case you forgot about. So if you have a question, just write it on the chat before you forgot. And then Doc is gonna make sure to answer it at the Q&A. Okay. Now introducing our next speaker, Moses Motaung. Moses Motaung is a director at re-energise Energy Africa, a company that provides specialized operation and maintenance services in biogas industry. Re-energise Africa expertise spans from end-to-end product conceptualization, ensuring waste to energy projects are both technically sound and profitable, to the supply of critical spare parts, gas cleaning systems, activated carbon solutions, and locally built filters. The company also provides oxygen nitrogen generators, strengthening the reliability and efficiency of biogas operations. With this leadership role at re-energise Africa, Moses brings a wealth of practical insight into both technical and operational dimensions of biogas projects, development and management. Today, he will share his perspective on innovations in biogas technology and how these innovations are shaping the industry future. Because biogas is an industry that's rapidly changing, and then with growth in specific technologies, there's expected growth in the industry as well. So it's going to take us through the technologies. Just now, Moses, you can share your presentation.
All right, thank you. Thank you, Doc, for a wonderful presentation. So I think it's hard to follow what you have put up, but I'll try. As Tusang has indicated, my name is Moses Motaung. I work with Tariq Hopena. We're both directors of re-energise Africa. So today, my presentation is gas quality. So we basically just looking at a narrow view. We're taking like a sort of a flow chart type of process from a biodigester to a cogen, which is a combined heat and power generation plant. So we're looking at gas quality that ensures that your cogeneration plant works effectively, it's reliable, and it's able to generate the energy that you are selling, or if you are the owner, you know, you're getting the best out of your equipment. So that's basically that we're looking at, just basically gas quality. So the scope of the presentation covers sewage gas, landfill gas, biogas, and mining gas. So these are the gases that we will term biological gases. We're looking at we're looking at their quality and how their quality impacts CHP, which is combined heating and power generator. We taking gas treatment as a black box, but I will go slightly inside to, like we mentioned, what equipment we're using and then how it works, but not into great detail, but we'll give you a feel of what each of the gas treatment modules along the chain does. So here we have a slide that shows the analysis of a sewer gas, biogas, landfill gas, and a typical requirements of a CHP for these gases. So the top half, it's basically the normal components which are not critical for CHP as long as you know what it is, and then they are able to set it up for the right CV of the gas that you are putting into it, then you're okay. But of concern or the topics that interest gas treatment are basically the trace elements that you find in these gases. Obviously, red, shows not a good sign for this. Green is good, and then yellow and orange. So if you look at this, the sour gas, or let me just say first, the trace element of concern here are H2S, which is present in all of these gases, silicon compounds, hydrocarbons greater than C5, and then of course water. So these are the things, the elements that we're looking at when we talk about gas treatment. So we're trying to remove those things. So we'll be touching on the technologies that we use for this elements. So you can see the normal biogas that we use, it's much better, like in terms of trace elements as compared to the sour gas and the landfill gas. So the sour gas of importance, there is the silicon compounds. Obviously, if you look at the average there of H2S, it's less than 75 ppm, and then if you look at that in relation with what this typical CHP requires, which is less than 100 ppm, so you're looking good there. But if you look at the silicon compounds, average is greater than 10 milligrams per cubic meter, and we are looking at the CHP requires less than 5, so that's one element of concern. And then the rest is okay. I'll go now to the landfill gas. You can see now the average H2S is 375, which is much more than what is required by CHP. Silicon compounds also sometimes also greater than 25, while we require less than 5 milligrams per cubic meter. Hydrocarbons greater than 600 milligrams per cubic meter. And the relative humidity required by CHP is less than 60%. So these are the things that we need to, the specifications that we need to take into consideration when we are applying gas treatment. So before we jump into the actual treatment itself, I have a few slides that has pictures. This picture shows you the impact of the trace elements that I have looked at, and then you will understand why we need to actually pay special attention in removing them or limiting them, such that they don't inhibit the operation of the CHP. So here we have a blocked silencer at the exhaust due to the siloxanes. This blockage will actually create back pressure, which makes your engine lose power. And then when it loses power, obviously, the yield from your generator also is handicapped. So you're not getting the full output of your generator. So if you are selling the electricity, you are not getting enough. The second one here, we're looking here at the turbocharger. You can see the turbocharger is also on the gas drain, on the exhaust gas drain. So it's basically a turbine that's that is driven by the exhaust fumes from the engine. So you can see the white or the grayish incrustation on the blades. This also impacts the functionality of the turbocharger. In some cases, the bearings can actually be damaged, and then you don't get the compression that is required, and this will lead to a loss of power of your gas engine. Those two which I've shown you now, they affect the performance, but this one now, when you have like incrustation like this on the pistons, valve trains, and then spark plugs, can actually lead to actual breakdown of the CHP. And for you guys here, you know that in the greater scheme of things, your CHP is, even though the digester is the heart, but the CHP is the one that's the most expensive and the one that's more maintenance intensive, and that's where money changes hands in terms of energy that is being sold. So it's an equipment that you need to look after to ensure that its operation is efficient and it lasts longer. It doesn't cost you much in terms of breakages or downtime, and then inability to produce the energy that you are selling. So you can see now, the deposit on the cylinder head. This deposit will require that you change the pistons quicker. You can see 3,500 hours as compared to 16,000 hours. So this is a problem because each downtime like this takes time, meaning that you lose valuable production if you're not treating your gas. The same here, still on the cylinder head, you can see again the same thing that we're talking about. These are basically the valves, inlet and outlet valves on the cylinder head. With this incrustation might prevent the valves to function properly, maybe open, not closed, thereby losing power of the engine. So just to give you a summary of problems by each of the impurities that we talked about: moisture, because we have hydrogen, we can get sulfuric acid forming if this moisture comes out of, if it condenses. So we need to remove moisture. We do get deposits in the gas control system from moisture in the gas, which then leads to malfunctions in the equipment. You can get pipe blockages. It can actually reduce the efficiency in the entire system, where you have water puddles, your gas transmission doesn't go well, and then you might get your CHP being stuffed or having vibrations because of oscillations in gas flow. Hydrogen sulfides together with water, you can get acidification of engine oil. It can increase. If you have acidification, means then your oil changes increases, then you have higher oil consumption, which is costly due to the cost of the oil itself, but also the downtime of the equipment. There's a risk of CHP damage through bad oil, deposits on piston and spark plugs, deposits in the exhaust system that we have already seen on the pictures, higher risk of corrosion in the entire system. So this is one of the key elements that we deal with on daily basis on the biogas plants. Siloxanes, heavy deposits in the combustion chamber. We've seen the pictures, increasing wear of parts because your bearings, your blades for the turbochargers, and then also the incrustation that forms on the cylinder can score the inner side of the cylinder, or on the cylinder heads can score the inside of the cylinder. So we can have increased breakdowns of the CHP, which is not desirable. So if we look at the water removal from biogas, you can see we use the Molia diagram, which we use normally for HVAC. The table that we have here shows the amount of water the gas can retain at different temperatures at constant pressure. So mostly we run the chiller to remove water from gas. We pass the water through a water chiller, which will then condense most of the moisture. We run the chillers around 10 degrees Celsius, and you can see it's between the water that can be held there, it's between 2.5% and 1%. So we remove most of the water there and then dump it to make sure that the gas doesn't have a lot of condensate. So the other thing that's important with this process is that other impurities are also removed with condensate. So things like ammonia gets removed when you remove water from gas. Hydrocarbons are also removed, C5s, and then some of the siloxanes also are removed with this process. So it's a process where you hit you hit a number of birds with one stone. I'm not going to go into the calculations for now because we don't have enough time, but I would like to cover all the other things. So the next thing now is the hydrogen sulfide. So the first step to remove this, you can add ferric substances into the digester. So you can start at the digester. You can see that the reaction that you get when you put a ferric material, you will actually break down you'll break down the sulfur to the elemental sulfur, and this can be a reduction at source, basically in the digester itself, or apologies, or you can have a biological desulfurization, and which is typical for agricultural anaerobic digesters. So you can have biological desulfurization where from 500 to 700 ppm of hydrogen sulfide can be reduced down to 20 to 80 ppm, which is quite good. If you remember how much we needed, the CHP required less than 100 ppm of H2S. So the last stage of which we specialize of is activated carbon filter. So this is the second stage. This can handle sulfur up to 2000 ppm down to 0 to 1 ppm by using activated carbon together with oxygen. So basically, activated carbon is just a carbon material that has been doped with a catalyzer, which enables oxygen together with hydrogen sulfide to react to form elemental sulfur, and then also water. So the sulfur itself, it's absorbed in the activated carbon, so it's get held behind while the water is dissolved into the gas, so it moves with the gas as vapor. So the gas must be dry, so you cannot actually treat with activated carbon a saturated gas. So in most cases, where you have, say, for instance, you have either a compressor or a blower just after the chiller, that will help with increasing the temperature of the gas to reduce relative humidity from 100 to between 50 and 60, because that's what we desire. But if you don't have that, a compressor or a blower between the chiller and the CHP, you can actually use a heat exchanger to make sure that you reduce the relative humidity of the gas. So oxygen is required for desulfurization, as you can see as per the equation here. So at this point in the gas, in the in the gas that goes into the cylinder that you see here. This is an activated carbon filter cylinder. So we inject oxygen of between 0.5 to 3% to enable the reaction to take place. So that's one of the key hydrogen sulfide gas removal. The next one is silicon removal in biogas, sewage gas, and landfill gas. So silicons, as the statement indicates, that there has been about between 6 to 7% increase of silicon. This is due to the following applications: substrates because it's used as a substrate for cosmetics, foaming, suppressors in detergent, repellents in building materials, automotive and leather care, and hydraulic and transformer oil. This uses silicon, and we find this in the landfills. They go into our water systems, so hence sewage gas and landfill gas will have more of this impurities. So during combustion in the engine, silicon together with oxygen forms silicon dioxide, which is quartz, which is now the incrustation that you saw on the pictures or the images that I've shown, that develops in the exhaust or the exhaust system of the car, of the engine, gas engine. If there's higher siloxanes in the system, I have indicated that during condensation of or removal of water or moisture in the gas, some of the siloxanes leaves, and then also partially some of the siloxanes, we can deal with some of the siloxanes in the activated carbon filter, but this depends on the concentration. So if the concentration is high and we want to use activated carbon filter to deal with the siloxanes, so we use a different formulation of activated carbon filter for this that will deal with both at the same time, silicon and also H2S. The slide here just shows you the absorption of siloxanes on the adsorber, which is now the activated carbon filter or activated carbon material. So it gets left behind, attached to this to the adsorbents. So here we can have complete gas cleaning from above 1,000 milligrams per cubic meters to 1 milligram per cubic meter of H2S and siloxanes, so which is quite a very efficient system. So the scope of supply basically looks at at the digester, where you can use a ferric material to remove sulfur or to treat H2S, and then a chiller together with the heat exchanger that removes the moisture, the condensate, which is the moisture removal, and then we have the compressor, which reduces relative humidity from 100% to between 50 and 60%, and then we have here now then the filter, activated carbon filter, that will now deal with the sulfur, which will break down the H2S to elemental sulfur that gets adsorbed on the filter material, and then the water that's produced goes with gas to the CHP. That's gas drying process. So this is just a picture of what a gas dryer looks like. It's basically a chiller at the bottom, and then there's a heat exchanger that gets cold water to cool the gas that flows into the pipe. And then here we have the blower station. So this is gas compression, which leads to a higher temperature, basically. Still a blower itself. And then there's a number of blowers for a bigger plant. And then gas cleaning, which is now an activated carbon filter picture. Here you can have a system that has parallel systems which you can be able to run two at the same time, and then if you want to service one, you can do that live. You just swap the valves to have another set running, so that you don't stop your plant while you are servicing these things, because the filter does get saturated. Then we need to remove it and then put a fresh filter to start the cycle again. So just to show you in terms of, this is a slide from my friend, my business partner, Tariq, showing in euro terms what it means to treat your gas. If you don't treat your gas, this is, you're looking at roughly 62,000 euros in terms of things like oil changes, spark plug changes, overhaul of cylinder heads, and then emergency maintenance, and then the labor cost that goes with doing this work. You can see clearly that having the gas treatment equipment between the biodigester and the CHP can really reduce costs. And I know these are just the costs of doing the work, but imagine the downtime and then the amount of gas that could have been generated and then been sold or been converted to electricity. Even the cost is actually even more, the lost cost of sales for this much. So I think that captures in financial terms the impact of gas treatment. So these are the benefits of properly designed gas treatment systems. It increases the CHP reliability, means that you have less downtime. You also have a higher system availability. We want higher system availability because this is the machine that produces money for you. Reduction of maintenance costs. We have seen the cost now, how much 19,000 euros compared to 62,000 euros. You have a longer life of CHP, which is it delays the replacement of this machine, which is what you want. You would like to get the value out of your expensive equipment. It also helps with the compliance with fuel specifications. So with the CHP plants, the OEMs will actually give you the specifications, as we have shown you in the earlier slides, that the gas that is required should have certain amounts. It puts a limit to the trace elements, and then if you are not able to meet those trace elements, it will definitely become an issue if the equipment breaks before time, and then the OEM will refuse to actually honor the warranties and guarantees because of specifications. So our gas treatment equipment helps you meet the specifications so that you can maintain the warranties and also have the longer life of the equipment. Yeah, that's in essence what we have. This is the equipment that we supply as re-energize and also maintain for our clients. And here are our contacts, my partner, and then myself. Thank you.
Thank you, Moses, for a beautiful presentation. I like that your company also works with hydrogen sulfide, which is a very problematic gas that's byproduct of the biogas process. I mean, it can even damage the infrastructure that you use in your plant as well. So time for the Q&A.